Hey guys, so we are back with another exercise. So let's look at this exercise. Now this one is it's simple. If you just follow what we've been talking about. So let's first of all read the question and let's see where this takes us. Donc soit f et g, les sous-espaces vectoriels de R3. F et g sont des sous-espaces vectoriels de R3. I will leave it to you guys to verify that F and G are indeed les subspaces of l'espace R3. Ok? Donc, donner une base de F, une base de G, on déduit leurs dimensions respectives. Ok? So we're supposed to find a basis of F, a basis of G, and then we also find their dimension. Their dimensions. And then exercise number 2 says, donner une base de F inter G et donner sa dimension. So même chose, we give a base for F inter G and then we give its dimension. Troisième exercice, montrer que la famille constituée des vecteurs de la base de F et des vecteurs de la base de G trouvés en 1 est une famille génératrice de R3. And then the question is, est-elle libre? Ok, bien. Exercise number 4 says, les espaces F et G sont-ils supplémentaires? Ok. Right. So let's look at the first exercise. The first exercise, we're supposed to donner une base de F et une base de G, and then we deduce their dimension. So let's look at une base de G. Une base de G, c'est quoi? Une base de F. Une base de F, c'est quoi? Base de F is going to be a family of vectors that is à la fois génératrice, which means they can generate the entire space F, and then libre. That is, they're supposed to be linearly independent. So we're supposed to find a family of vectors that satisfies these two conditions, génératrice and libre. Now, whenever you're given whenever you're given this kind of questions, what you're supposed to do to be able to find a base of F or a base of G, you're supposed to take a vector in F. If we're looking for a base or a basis of F, we're supposed to take a vector in F and see how that vector is going to be decomposed. Okay, we take a vector in F and then we see how that how that vector is going to be decomposed. So let's first of all, maybe let me just write that as a comment. Let me just put it here so that you can maybe see what is happening here. So to find a basis of some subspace, all you have to do is to take a vector in the given subspace, and find its decomposition. So this is the general method, find its decomposition. So if you do that, maybe let me just change the color. Maybe let me just choose red like so, because it makes it a little bit visible and makes it stand out from the rest of the text. So let's look at exercise 1. So we take a vector from F. Since we're finding a base for F, we take a vector from F. Since we're finding a base, okay, we take a vector from F. Bien. So we're going to say soit U, which is so x, y, z, like so, up. X, y, z in F, we take a vector U, x, y, z in F, and then what does it mean for this vector U with components x, y, z to be in F? So it means that it satisfies this condition that we have here. So x minus 2y plus z is equal to 0. Now we need to look at how this vector that we've taken in F can be decomposed. So you first of all, since you have one equation here, only have one equation here, the first thing that you're supposed to do here is to make one of these variables the subject. Now you can make x if you want, you can make 2, you can make minus 2, you can make y if the subject of the formula if you want, you can make z the subject of the formula if you want. Now it is recommended that you choose either x or z because their coefficient is 1. They have a coefficient of 1. meaning it's going to be very easy for you to, you get simpler vectors like that. If I attempt to make y the subject of the formula, I will get fractions. Okay, we want to avoid fractions, you know, whenever it's possible. Whenever it's possible, we want to make sure that we avoid fractions. So I'm going to make x the subject. So here we're going to say x is going to be equal to 2y minus z. It's the same equation. X is going to be equal to 2y, okay, minus z. So we found x, okay. So let me just maybe write this vector in column form, the vector that we're supposed to decompose. So x, y, z. So we only have one equation, and then this one equation, by making x the subject, we've been able to see that x can be written en fonction de y et de z. So we're going to have 2y minus z, like so, and then y, and then z, like so. This is going to be equal to, like so, 2y minus z, and then y, z, like so. Okay, so since you've written all the vectors, if you look at all the vectors that we have here, they've been written en fonction de y et z, en fonction de y et z. Okay, so we need to further decompose. We need to further decompose this. So since here you have two variables, y and z, to find the first vector that we're supposed to put here, the first thing that you do is you take z is equal to 0. Okay, you take the second one, z is equal to 0, and then you only be left with the first one. So you have 2y, like so. So z is equal to 0, so y, so z is equal to 0, and then plus, like so. Now since we were from taking z is equal to 0, we're going to say y is equal to 0. If y is equal to 0, we're going to get minus z, and then here we're going to get 0, and then here we're going to get z. If you add these two vectors, you would get back, if you add these two vectors, you get back to this vector that we have here. So 2y plus minus z is 2y minus z, and then y plus 0 is y, and then 0 plus z is z. C'est très facile, okay? Okay, now that we've written, you know, these simpler vectors, we will need now to factor out by the common variable. So here we see that we can factor out a y, like so, and then here we're going to have 2, and then 1, 0, and then plus, like so. We're going to factor out a z, like so. Then we're going to have minus 1, and then 0, and then 1, like so. Right. So this vector that we have now here, we're going to call it v1, and then this vector that we have now here is v2. So this is going to mean that actually f is going to be equal to vect f, because our choice of this vector xy and xy z because our choice of this vector u is arbitrary. It means that actually f is going to be equal to vect of you know, these two vectors. It's going to be equal to vect of these two vectors, which is, the first vector is 2, 1, 0, like so, minus 1, then 0, 1. So in other words, we are saying the family of vectors, la famille V1, la famille V1, V2 est une famille génératrice de quoi? Est une famille génératrice de f. So we're supposed to find the base. So the first condition of generatrice has been satisfied. We're supposed to find the base. Okay, we're supposed to find the base. So the other thing that we must show is that the two vectors, we're supposed to check if the two vectors are linearly independent. So to be able to check that two vectors are linearly independent, what do we normally do? So remember that we take scalars, soit alpha 1, alpha 2, alpha 3, three scalars that we take from R3, like so. So and then we suppose that the combination, here since we only have two vectors, we take two scalars. Since we only have two vectors, so we'll suppose that alpha 1 multiplied by v1 plus alpha 2 multiplied by v2 is equal to 0. And then what is our goal? Our goal is to show that alpha is equal to, alpha 2 is equal to what? Is equal to 0. Okay, so let's do that. Alpha 1, and then let me just maybe get back to the original color. So alpha 1 multiplied by, what's the first vector? The first vector is 2, 1, 0, like so. And then what's the second vector, or the second vector is minus 1, 0, 1, like so, is equal to 0. So if you multiply by the scalars and add, you are going to have 2 alpha is equal to, you're going to have 2 alpha alpha 1 minus alpha 2, and then here you're going to have alpha 1. Then for the last one, you're going to have alpha 2. You're going to have alpha 2, like so. Okay, then this is going to be equal to 0, 0, 0. So this vector is, you can say, it's the 0 vector in R3, so that you don't confuse things. So two vectors are equal if and only if their corresponding components are equal. If you look at the second line and the third line, you see that alpha 1 is going to be equal to 0, and then alpha 2 is also going to be equal to 0. So you can see that alpha 1 and alpha 2 are equal to 0, and this is going to mean that la famille V1, V2 est libre. Now look, this family of vectors, this family contains vectors that are linearly independent and that generate the space F. So this is going to, c'est donc une base de F. So if you look at F, okay, since you now have a base V1, V2, what is the dimension of F? So the dimension of F is going to be the cardinality of this family of vectors that we have here. So V1, V2, like so. So the cardinality of this family of vectors. So what do you think is the cardinality of this family of vectors? So the cardinality is just counting the number of vectors we have here. So the dimension of F is going to be equal to what? It's going to be equal to 2. C'est très simple. Like so. Okay? J'espère que ça va. So this is what we have. The dimension of F is going to be equal to what? It's going to be equal to 2. Now let's look at how we can find une base de G. C'est très facile. So we're going to do the same thing. We take a vector, we take a random choice, of a vector in what? In G. And then we'll look at how that vector is decomposed. So just like we are saying here, to find the basis of some subspace, take a vector in the given subspace and find its decomposition. Okay? So let's do that for G. Let's do that for G. So let's maybe look at the condition that we're supposed to check. 2x minus y plus 2z. Right. Okay. Right. So maybe you can say 1b. The first one is 1a. So we'll take a vector x, y, z in G. Okay, we'll take a vector x, y, z in G. So this means that we satisfy this condition. So we have 2x minus y plus 2z is equal to 0. So just like the first one, here you only have one equation. So you are free to make x or y or z the subject. Now it's advised that you make y the subject because the coefficient of y, it's minus 1 here, but it's not going to give us fractions. And then if I make y the subject here, I'm going to have y is going to be equal to 2x plus what? It's going to be equal to 2x plus 2z, like so. And then now this vector that I've taken from G that has 3 components is going to be, so the x is going to remain x, but then the y is going to be replaced by 2x plus 2z, like so. Then the z is going to be z because we've made y subject here. So you can see that just like in the first case here, we have 2 variables, x and z. So we take z is equal to 0. So this is going to give me x. Then this is going to give me 2x. Then this is going to give me a 0 here. And then plus. Then we take x is equal to 0. And then this is going to give me a 2z here. Then this is going to give me a z here. Like so. Hopefully that is clear. Now we can factor out an x here. So this is going to give me 1, 2, 0, like so. And then plus we can factor out a z here. Then this is going to give me 0, 0, 2, and then 0, 2, and then 1, like so. So this is our vector V1. Now we've used, we've used a lot of V's already. Let's maybe use another letter. Let's take W1 and then W2, like so. Okay. So this means that G is going to be equal to vect. G is going to be equal to vect of the two vectors. That is 1, 2, 0, like so. And then remember that if, let me just remind you what the vect means in case you've forgotten. Here the vect means that every vector in the set G can be written, every vector in the set G can be written as a linear combination of these vectors that we have here, W1 and W2. Okay, that's what vect means. In other words, we are saying that la famille, de famille W1, W2 est une famille génératrice, génératrice de G, like so. But is it libre? That's the next question for us to have a base. Is it libre? So here it's wrong for you to conclude directly that c'est une base, because this only shows, this only proves that this family of vectors, c'est une famille génératrice. C'est une famille génératrice. Okay? For us to determine une base, we have to check the second condition, which is linear independence. Now, I'll leave it to you guys to check, but these two vectors are libre. These two vectors are libre. So you can sort of like do whatever you can do. You can repeat the same process here. You check, you find that these two vectors are libre. Why? It's because there's no way of compensating for this 0 that I have here. There's no way of compensating for this 0 in the second one here. Okay, there's no way of compensating the second. There's no way I can find a scalar alpha such that this 0 that we have here is going to be compensated for. Okay, but you can check if you want. Okay, even this 0 that we have here. Okay, there's no way of finding a scalar such that I compensate for this 0 here. Right. So la famille, I'm just going to write the conclusion, but I'll leave it for you guys to check. So maybe I can sort of like remind you here that I've just sort of like, you know, checked and sort of like I've sort of like seen things, seen the vectors, and I've deduced that, okay, I've observed, solved it in my head that, okay, the vectors are not linearly independent. Donc la famille W1, W2 est libre, car W1 et W2 ne sont pas collinear. They are not collinear vectors. So hopefully you remember these terms. So we've been using these terms. Okay, so we have libre and then we have génératrice. It means donc this family of vectors W1, W2 est une base de G, like so. And then if we're looking at the dimension of G, well, it has to be the cardinality of this family of vectors, W1, W2, like so, which is going to be equal to what? Which is going to be equal to 2. So the dimension of G in this case is going to be equal to what? Is equal to 2. Right. Third exercice. So third exercice is saying, montrer que la famille constituée des vecteurs de la base de F et des vecteurs de la base de G trouvés en 1 est une famille génératrice de R3. Okay? And then here they're asking the question, is this family of vectors libre? Now, let's first of all look at what we've done so far. So what we've done so far shows that we have a basis for the first espace, which is F. We also have a basis of the second espace, which is G. If you remember, when we take the sum of the two vector spaces, we'll generate another subspace of the parent space. Okay, we'll generate another subspace. So third question. So F plus G, if I look at this basis here, if you look at this basis, the union of the two, the union of the two, la base de G et la base de F. If I take the union, I'm going to have a base of the sum, which is F plus G. Okay? Hopefully that is clear. So this family of vectors that we have here, this family of vectors this family of vectors, let's say the W1, this family of vectors which is going to be formed by the union of the two basis systems, so which is the first one was V1, V2, and then W1, W2, like so, est une famille génératrice de quel espace? Est une famille génératrice, est une famille génératrice, est une famille génératrice de F plus G. So we wrote it in the notes that if I sort of like take the union of these two basis systems, so if you found the bars for F, and you found, if you found the bars for F, and you found the bars for G, which is, you know, the two spaces that we have so far. If you found the bars for F, and you found the bars for G, I think I've actually skipped a question here, which is the second one, but no problem. So we can solve. We can jump from the second one to the third exercise. Then we'll get back to the second one. Just, you know, we give it a bit of time, so we can actually solve. The third question does not depend on the second one. So if you found the bars for F and you found the bars for G, if you take the union of the two bars that you found, that is V1, V2, these vectors are coming from the basis of F, and then W1 and W2 are coming from the basis of G. If you take the union of these of les deux bases, you're going to get a famille génératrice of this subspace, which is F plus G. That's the règle générale. If you take the union of the bars of F and the bars of G, which is what I've done here, you come up with a famille génératrice of this espace F plus G. Now the question here is saying, montrer que la famille constituée de vecteurs de la base de F et des vecteurs de la base de G trouvés en 1 est une famille génératrice de R3. So another way of writing what I've written here, V1, V2, W1, W2 est une famille génératrice de F plus G. Another way of writing this is saying that F plus G is equal to vect of these vectors V1, V2, V3, W1, W2, so V2, then W1, W2, like so. So F plus G is equal to vector of this. So the goal is to show, let me just remind you what the question is saying. The goal is to show that this R3 is also going to be equal to vect of V1, V2, then W1, W2. This is what we're supposed to show. Okay? In other words, we're supposed to show, we're supposed to show that this espace sum, this sum of the two vector spaces is going to be equal to R3, like so. This is what we're supposed to show. Right. Let me first of all repeat what I've said here. So we are saying, if you take the union, the question is talking about the union of the basis of F and the basis of G. Normalement, if you take the union of the two bases of the deux bases that we found for F and G, that is the union of the bars of F and the union of the bars of G. If you take the union, you get une famille génératrice of the sum of the two vector spaces, which is F plus G. That's règle générale. Normalement, this is what you're supposed to get. So in other words, we are saying that if I take the union of these two basis systems, of these the deux bases that are found for F and for G, if I take the union, then I'm going to get une famille génératrice de F plus G. In other words, we are saying that F plus G is equal to vect of the vectors V1, V2, W1, W2, like so. But then the question is saying we must show that the union, this same family of vectors, c'est une famille génératrice de quel espace? De R3. So in other words, we're supposed to show that R3 is equal to vect of V1, V2, W1, W2. In other words, we're supposed to show that F plus G is equal to R3. Like so. Hopefully, you're able to understand. Now, two vector spaces are equal if and only if. So let me first of all remind you that in algebra, when we're talking about les ensembles, how do we show that two sets are equal? So rappel, so this is just a rappel. So if A is equal to B, A is equal to B is equivalent to saying that A is a subset of B, and that B is a subset of A. So this is what we said. However, here you can do the same thing if you want. You can show that this F plus G is included in R3 and that this R3 is included in F plus G. However, we won't use this method. We won't use this method. Here in linear algebra, to be able to do the same thing, in linear algebra, so let me just say to do the same thing in linear algebra, to do the same thing in linear algebra, what we have to do is that we first point is to show one inclusion. Show only one inclusion. Show only one inclusion. Show only one inclusion. And then the second point is to show that the two spaces have the same dimension. So if we were in sort of like, if we were talking about les ensembles and we want to show that two spaces are equal, we would have to show that the first set is included in the second set and that the second set is included in the first set. But to do the same thing in linear algebra, what we can do is that we show one simple inclusion. We show one inclusion, only one inclusion. Either we show that this F plus G is included in R3 or that this R3 is included in F plus G. So you can choose any inclusion you want. And then the second point is to show that the two spaces have the same dimension. So the first point here is clear. That if you look at F plus G, if you look at all the vectors here, if you look at all the vectors v1, v2, w1, w2, all the vectors have three components, right? All the vectors have three components. v1 is an element of R3, v2 is an element of R3. So v1 is an element of R3, v2 is an element of R3, w1 is an element of R3, w2 is an element of R3. So you can see that it actually makes sense that we say that F plus G is also is included in R3, okay? Because all its vectors are members of R3, okay? All the vectors in F plus G are elements of R3. So the simple inclusion that we can show here is that, so here I'm going to take this and put this here and maybe change the color. So we show one inclusion. So let's remember what we have. We have F plus G is equal to R3. So we want to show that F plus G is equal to R3. So we show one inclusion. So it's clear that, so trivial. So it's clear that F plus G is included in R3. Why? If you look at all the vectors that are in F plus G, if you look at all the family of vectors, if you look at all the vectors in this family, V1, V2, W1, W2, they all have how many components? 3 components. And all of those vectors are elements of what? Of R3. So you can actually understand that this space is going to be a subset of this space. And then the other thing is that we have to show that the two spaces have the same dimension. So to be able to find the dimension of, we already know the dimension of R3. On sait que the dimension of R3, the dimension of the espace R3 is equal to 3. Well, this is well known. But what do you think is the dimension of the subspace F plus G? So we have to use formule de 4 dimensions or the formule de Grassmann. So that's what that is what is going to help us. So it is the dimension of F plus G is equal to the dimension of F plus the dimension of G minus the dimension of F inter G. Okay? Now, remember that we don't know the dimension of the intersection, but because we skipped the second question. Okay, it's because we skipped the second question. So what we're going to do is that we're going to quickly solve the second question and then come back and plug in the dimension. Okay, and plug in the dimension. But first of all, before we go to the second exercise, let's look at what we have so far and what we've said. The question is saying, let's read the question one more time. The question is saying, montrez que la famille constituée des vecteurs de la base de F et des vecteurs de la base de G trouvés en 1 est une famille génératrice de R3. So, normalement, if you find the union of the vectors in the base of F and the base of G, you're going to find une famille génératrice de F plus G. So here, F plus G is going to be equal to vector of this family of vectors, which is V1, V2, W1, and W2. Now, F plus G is equal to vector of this family of vectors if every vector in F plus G can be written as a linear combination of the vectors V1, V2, W1, and W2, like so. Okay? So, normalement, that's what you get. If you find the union of the vectors in the base of F and in the base of G, you find une famille génératrice de F plus G. Now, the question is saying, we show that this family of vectors est une famille génératrice de quel espace? Of the espace R3. So we're supposed to show that R3 is equal to vector of V1, V2, W1, and W2. In other words, we're supposed to show that the espace F plus G is equal to R3, like so. Oh, in les ensembles, to show that two spaces or two sets are equal, we are supposed to show that the first set is included in the second one and that the second one is included in the first one. But we can do the same thing in linear algebra by first of all showing only one inclusion. Either we show that F plus G is included in R3 or that R3 is included in F plus G. And then for the second point, we have to show that the two spaces have the same dimension. The two spaces have the same what? Have the same dimension. That's what we have to do. Okay? So this is going to be equivalent to performing this operation that I've written here. A is equal to B is equivalent to saying that A is a subset of B and that B is a subset of A. Okay? So it's clear that the espace F plus G is included in R3 because if you look at all these vectors, V1, V2, W1, W2, they all have three components. So a priori, they are elements of R3. So we can see that F plus G is going to be included in what? In R3. How about the second point where we have to show that the two spaces have the same dimension? Here on sait que the dimension of R3 is equal to 3. En général, the dimension of Rn is equal to n, like so. Avec n, un entier that is différent de 0. Okay? So here we know the dimension of F because we calculated in base to F. We also know the dimension of G, but then we don't know the dimension of what? The dimension of F intersection G. So let's find the dimension of F intersection G. So I'm going to sort of like group and put the two exercises together. Exercise 2 and exercise 3. The exercise 2 is skipped and the exercise 3. Exercise 2 is about finding a base of F inter G. Finding a base of F inter G. So to find a base of F inter G, just like we did for F and G, we'll take a vector in F intersection G and look at how that vector is going to be, decomposed. So we're going to say trouvons une base de F inter G. So soit, c'est bon? Soit, okay, let me just maybe go down a little bit like so. Let me just give myself some space. So soit we take a vector U, soit U with components X, Y, and Z, an element of F intersection G. So what does it mean for this vector U to be in F intersection G? Well, this means two things. Well, this means that this vector U is an element of F and that this vector U is an element of G. So it means the vector U satisfies the condition in F and the condition in G. The condition in F is X minus 2Y plus Z is equal to 0. Then the condition in G is 2X minus Y plus 2Z is equal to 0. So how are we going to sort of like solve this system that we have here? C'est très facile. So the first thing is what we're going to do is that we're going to look at the first line. I'm going to call it la ligne 1. The second line I'm going to call it la ligne 2. Just like we just like we did for the first two exercises. What we're supposed to do here is going to be similar. What we do here, we do the same thing here. So we keep the first line constant. We don't make any changes to the first line. So we leave the first line the way it is. We leave it the way it is. So X minus 2Y plus Z is equal to 0. But then for the second line, we're going to eliminate the x that we have here. So to be able to eliminate the x, what operation are we supposed to perform? What operation are we supposed to perform here? C'est très facile. C'est la ligne 2 reçoit la ligne 2 reçoit la ligne 2 minus 2 times. We have to be very careful here, because the second line here we have x has a coefficient of 2. So we have to make the coefficients equal and look at the operation we're supposed to apply to get that which we expect. Okay? So here I'm going to say 2 multiplied by la ligne 1. Bien. So la ligne 1, I've multiplied. So here 2x minus 2x will give me 0, and then minus y, minus y, and then here if you multiply you get a 4, right? So you have minus y minus 4y. So you get minus y plus 4y, which gives you 3y. Okay, here we're going to get 3y, like so. Then the other part will also be, the coefficients are going to, the coefficients for z will be equal in magnitude, because you have 2 multiplied by z, which is 2z. If you take the difference, you get 0. So here, what we get here is going to be, so what we get is x minus 2y plus z is equal to 0. And then you can see that actually this is going to mean that y is equal to 0. Well, if y is equal to 0, then if y is equal to 0 in this particular case, so with these two equations, we cannot find z. With these two equations, we cannot find z, right? So z stays the way it is. Z is equal to z. But then y is going to be, if y is equal to 0, we can plug the value for y here. We can put it here. So you're going to get x, and then plus z is equal to 0, and then y is equal to 0. Z is equal to z, because we cannot find the value of z with these two equations that we have here, because z has been eliminated as well together with x. Okay, so here you can make x the subject. If you make x the subject, what are you going to get? You get x. If you make x the subject, you get x is equal to minus z, and then you get y is equal to 0, and then z is equal to z. Now let's look at this vector x, the vector u, which is x, y, z. Let's look at how it's going to be decomposed. Well, the x is equal to minus z, according to what we found. The y is equal to 0, then the z is equal to z. So here we can factor out the z, and then you can have minus 1, then you have 0, and then 1. So this means that f inter g is equal to vect, of what? Of 1, 0, 1, like so. Oh, this is only one vector, right? It's only one vector. So if it's only one vector, this vector is libre. So 1, 0, 1. Of course, this is minus 1, sorry. Minus 1, 0, 1 est libre, because it's only one vector. It's only one vector. It's not calling it to any other vector. Est libre. Donc, est libre. So this is going to mean that minus 1, 0, 1, like so, est une base de quel espace? Est une base de f inter g est une base de f inter g. C'est une base de f inter g. Okay? So hopefully things are clear up to this point. J'espère que ça va. Up. So hopefully things are clear up to this point. So what would be the dimension of f intersection g? Well, the dimension of f intersection g is 1, because we only have one vector in the base. So now we know the dimension of f inter g. Let's go back to this exercise that we have here. So here the dimension of f is 2. The dimension of f here is 2. The dimension of f here is g is 2. The dimension of f inter g is 1. So 2 plus 2 is 4. 4 minus 1 is 3. So the dimension of f plus g is 3. So we've shown that f plus g is equal to R3. We've shown that f plus g is equal to what? To R3. So the conclusion here is the conclusion here is going to be that V1, V2, W1, W2 est une famille génératrice de quel espace? Est une famille génératrice, est une femme génératrice, like so, de R3, like so. Then the next question is, est-ce que c'est une famille libre? Est-ce que c'est une famille libre? Now here we have to think about one theorem qui est très très important. The theorem is that, let's look at R3. R3 has dimension 3, right? But then how many vectors do we have in this famille génératrice? We have 4 vectors, V1, V2, W1, W2. Now because R3 has dimension 3, it means it has a base that has 3 elements. The dimension of R3 is 3 because if you look at the base of R3, you can take the base canonic as an example. If you look at the base of R3, it is going to contain 3 vectors. The family of vectors that we have, V1, V2, W1, W2, has 4 vectors. So this family of vectors cannot be libre, because if a family of vectors, if a family E has a base that has n vectors, if a family E has a base that has n vectors, okay, you have to get what I'm saying here. You have to pay particular attention to what I'm saying here. If a family E has a base that has n vectors, any family that is going to be linearly independent, any family of vectors that is going to be libre, is going to have at most n elements. So let's look at R3. Here E is equal to R3. R3 has a base. R3 has a base that has how many elements? 3 elements. So it means that any family of vectors that is going to be libre in R3 has to have at most 3 elements. But if you look at this family of vectors, V1, V2, W1, W2, how many vectors do we have? We have 4 vectors. So this family of vectors can never be libre, because if it has to be libre, it has to have at most 3 vectors, because the dimension of R3 is 3, meaning it has a base that has 3 vectors. So this family of vectors est lié. So this family of vectors is going to be lié. So if it has to be libre, it has to have at most 3 vectors in the case of R3. So that is what we have here. C'est bon? Then the last question is also very simple. Les espaces F et G sont-ils supplémentaires? La réponse est non. Because if they have to be supplémentaires, they have to be en somme directe. They have to be en somme directe, meaning F inter G has to be reduced to the 0 vector. Okay? And E has to be equal to F plus G, meaning every vector in E can be written as a sum of, can be decomposed into an element of F and an element of G. Can be decomposed into the sum of an element of F and an element of G. Okay? This condition has been violated. This condition has been violated because if you look at the intersection, of F and G, we found this vector minus 1, 0, 1. This is different from the 0 vector. Because the 0 vector is this vector 0, 0, 0, like so. So we can see that the intersection is not reduced to the 0 vector. So these two spaces F and G are not supplémentaires. Alright. Hopefully that was clear. And I'll allow myself to move to the other exercise.